It's my honor and pleasure, I must say, to introduce Bob McPherron here today, who's probably one of the most accomplished space physicists that we have around, right?
Well, I hope so.
Yeah. And Bob and I, we go back, let's say decades, let's not be too specific on this. Those are really high numbers. So usually when you introduce someone, you ask for the CV, but what I did here was actually looking at your Google Scholar page, the most cited papers. So you have an H index of 78. You have 23,400 citations, so although what worries me is that the number of new citations is relatively constant about the last 10 years.
Well, imagine that. I retired.
Yeah, but the other thing that actually surprised me a little bit in the list here is that, okay, Bob, you're mostly known for substorms, right? And
Right.
so, but your substorm papers are actually not really at the top, So you invented the growth phase of the magnetic substorm, and that's number 7 paper, I think. You had a review paper that is number 5. You had these. What was this? The phenomenological model for substorms from not 70.
That was the main
number
one.
2. But your number 1 paper is actually the Burton paper, which is not substorms but storms. I mean, and that describes how storms react to the solar wind, right? There's a simple Burton formula, which of course has been used a whole lot. And of course, what really makes you famous, Bob, is your number 3 paper. That's the semi-annual variation of geomagnetic activity, which is also known as the Russell-McPherron effect.
Yeah. It's not everyone that gets something named after them.
Yeah, I mean, that is probably one of the most lasting things, because that will be around probably 1,000 years from now, right? So yeah, so on the formal introduction, yeah, you graduated from Berkeley, right, in in the 60s, right, 68. 68, together with other notables, right, with George Parks and Ferd Coroniti.
Right.
And I know there's a lot of history there, but I don't think we have the time to do that, So, I mean, you have been at UCLA basically for your entire career, retired about, I think, 10 years ago, right?
Yes.
Right, and but have been active since then, right? Okay.
Well,
And
I've only got 60 papers since then.
only 60. Oh man, I mean, that's a shame.
I didn't write them all, but I've participated in them.
Yeah, all right. Okay, I think I've said enough.
Okay.
So you'll be telling us about the solar wind coupling and magnetospheric substorms, right?
Right. I think you're looking at slide number 1 with the title on it. And you notice that this was the Van Allen lecture. And when I received this award, or at least the announcement, I said, what can I talk about? Well, what am I best known? And of course, you just told them it's substorms. So this graphic with that number over here on the left side of 10,000 is the cumulative number of citations per year that use the word substorm. And you see it grows very slowly since 1964, when Akasofu wrote the paper and published it, to 1982 when Geotail was launched. And from Geotail launch up until 2007, a much steeper curve, and then Themis launch up until the current time. And look at the number of papers. It's over 7,000 papers with the word substorm. And the total number of citations to those papers exceeds 166,000. So it's a high volume literature and very difficult to keep up. The problem today is that it's difficult to do anything really global and novel because so many people have worked on it for so long. Let me get... this is what I wanted to talk about today, and that is I have a view of substorms and the processes that are involved in them, at least for an isolated substorm, that involves 15 simple words. And if you know those words and their meaning, you pretty much understand how a substorm will work. So here's growth phase, and this is the expansion phase of the substorm. I don't deal with the recovery here. But in growth phase, increase in coupling, day-side reconnection, erosion of the magnetopause, flux transfer, lobe loading, current sheet thinning, earthward extension of the tail current. Then the expansion phase. It begins, as growth phase did, with reconnection, but in the tail. Then the ejection of a flux rope or plasmoid, bursty bulk flows to the Earth, the onset of the substorm or expansion, auroral expansion, the development of the substorm current wedge, synchronous dipolarization, and particle injection. So those are the topics of the figures that are going to come. I have a few more than 15, but at any rate, those are the concepts you need to understand in order to look at substorms. Let's start on the left side. In 1964, I had started my research at Berkeley, and I was going to accompany Kinsey Anderson's group with George Parks to the auroral zone to measure magnetic pulsations on the ground associated with electron precipitation. And we went up there and we flew, I think, 9 balloons. And I was measuring with big search coils on the ground, the magnetic pulsations. And we, out of those 9 balloons, only 1 got data. We watched the aurora overhead and wrote it down on our chart records and things, but we were very unsuccessful. And we came back to Berkeley, and in the fall of 1964, we found this paper by Akasofu titled, well, I don't have the title there, but it's the Auroral Substorm. And it was an organization in polar plots of the way the aurora develops in time and space. It was a phenomenological model of what you were seeing in the aurora. And both George and I got really excited, saying, that's just what we saw, just what we saw. So we returned in 1965 to the auroral zone to make more measurements. We were more successful, let's say, in our balloon flights and whatnot. And I made some mistakes. I got so excited, I set the dials on my amplifiers up and down. I changed the filters and whatnot. I got back and I couldn't make any sense out of it statistically because there wasn't a uniform sampling of the phenomena. But Akasofu published a second paper, the Polar Magnetic Substorm. So at any rate, I returned a third time to the auroral zone. I don't know if you've ever heard of this place, Flin Flon, Manitoba. And it's a very interesting place because it's the furthest south in North America that we get the auroral oval. It's on the geomagnetic prime meridian. My thesis title is down here, Relation of Auroral Zone Micropulsations, we now call them ULF waves, to magnetospheric substorms. Notice that I used the word substorms in my title. And if you come over to the left, you will see a time sequence diagram with the start of the expansion phase shown here. And these were 4 different types of waves. This turns out to be PC1 or ion cyclotron, irregular pulsations, I can't say, just electrojet noise bursts, which are really PI2, and band limited pulsations that merge into what we now call PC3 and PC4 in the day side. But the important point is, if you look up here, you'll see that even in my thesis days, I said growth phase. And the basis of that growth phase was really the probability of observing noise bursts. These are the data, these are some of the spectral analysis that I did in the thesis. But think about it this way, these are the original records. And in order to do this analysis, I had to digitize those records. And that was done by sitting, digitizing the trace of these chart records. It was a labor-intensive process, and I would never want to have to repeat it. What happened is some of our initial results, I went to a spring meeting of the AGU in Baltimore, and No, it was Washington, D.C. at the time, 1967. And I heard Neil Bryce give a talk. And he says, you know, this whole business about substorms, it's happening everywhere. It's a global phenomenon. And I came back and I talked with my colleague and co-graduate student, Ferd Coroniti, and he says, you know, it's really a magnetospheric wide, a magnetospheric substorm. And so based on that, this paragraph you see up here, we then generalized the concept of the auroral substorm to include the worldwide disturbance characteristics to emphasize the importance of magnetospheric auroral zone observations. And we called it magnetospheric substorm. And it stuck. So that was the start. Well, back to the growth phase. It was done with Pi2 pulsations, and this is a translation of that diagram that I had before. I hand scaled the thesis plots and redid them. This is the expansion phase, the white line at 0 time. And here's 60 minutes before. Notice how the probability of Pi2 bursts increases throughout this 1 hour interval. I said, this is an unstable system that is becoming, growing more and more unstable and finally goes off. I said, this is a growth phase. And so I wrote the paper with this diagram that you see here on the left as the main evidence, justification. And well, let's put it this way. 2 referees read the paper and 2 referees rejected it. And Alex Dessler, the editor, called me up and he says, Bob, he says, no way that we'll ever get one of these referees to accept your paper. The others opened a negotiation. So why don't we convert this to a brief report, and that way I can get by with only 1 referee. So I want you to negotiate with this referee. Well, the referee, when I called him, said, no way on earth will I accept pulsations as evidence for substorm behavior. I've got to see it in magnetograms, raw magnetograms. So what I did is I put together a chain. This is about as good as you could do at that time. Let's see, this is Sodenka's in Finland, Livergore, Iceland, Great Whale on wet shore of Hudson Bay, and College, Alaska. And the important thing here is you can see, if you come down vertically, the sharp onset of an expansion phase at Great Whale. And prior to that is the development of a negative bay at other locations. And the referee says, that's a growth phase. I accept it, and the paper was published. I must say that that was the beginning of 15 years of controversy. That every month almost, there was something saying, oh no, there is no such thing as a growth phase. Any rate, at the same time at Berkeley, my thesis, one of my thesis committee was John Wilcox, and he had a graduate student, one of my colleagues, Ken Shatton, that was working on the solar wind properties that were correlated with the magnetic activity. So here is my translation of one of their diagrams. It's the KP index from 0 to 9 along the diagonal here. And vertically is the strength of the IMF magnetic field, and horizontally the solar wind speed. And the interesting thing is, if you increase speed at a constant b, you increase Kp. Similarly, in fact, they're just diagonally. They're equally important, V and B. That was the conclusion they came to. They also looked at the correlation with BZ, and I've translated here into a study of the cumulative probability of observing AE as a function of BZ. And here's 0, and here's southward field. If you look at the median value for southward field, you'll get strong AE, and for northward fields, the median AE is virtually 0. In other words, you had to have a southward magnetic field in order to create magnetic activity. Well, there's a possible reason for this, and that was suggested by Jim Dungy in 1961. And his idea was magnetic reconnection. The idea that a magnetic field in the solar wind, anti-parallel to the Earth's dipole field, would be pushed against the day side and near the magnetic equator. Reconnection would start, the field lines would be cut, and the solar wind would transport them over the poles and into a long tail behind the Earth. And they would be pressed together at the center of the tail. They would reconnect, that's where the word comes from, and then flow back to the day side to flow into the X line on the day side. Here's a more modern view, 6 or 7 years later, drawn by Axford of the same thing. But Dungy never talked about time delays in the system. He kind of saw this as a static system, but it takes time for the influence of the reconnection to meet the ionosphere, L over R time constant. It takes time to transport to the tail. It takes time to get together. So there are time delays in the system. At any rate, at that point, Chris Russell and I were working together, trying to prove that magnetic reconnection really happened and that activity might be caused by reconnection. What was known for a very long time is that there was a semi-annual variation in geomagnetic activity. Magnetic indices would have the strongest amplitude near the equinoxes, 81 and over here 267 or something. So what we ended up arguing in this now famous paper that Jimmy mentioned is that let's assume that the magnetic field of the sun lies in its rotational equator and is drawn out by the solar wind. Well, the axis of the sun is tilted 7¼ degrees to the ecliptic. So we argued that the angle between the GSEQ, the solar equatorial y-axis, and the GSM y-axis, that's the Earth's dipole going around and around, will decide what fraction of the azimuthal magnetic field of the solar wind will be parallel to the z-axis in GSM. And this is a plot of that angle. And you can see there are two peaks. One, it isn't at the equinox. It turns out that tilt delays it about 10 days after the equinox, but it's 22 in the spring and it's about, well, 10 hours in the fall. It's also important to realize that these angles have signs, and that if you just look at the angle itself, it turns out to be annual variation, not a semi-annual. But the important thing is a rule that we came out of this work. It was called, we always quoted it as spring to fall away. In spring, an IMF to the sun will project negative and reconnect. And in the fall, it is a way field line that does it. So only half the time do you actually get the Russell-McPherron effect. But if you look over here, this is the actual data from about 50 years. And you see in the IMF BZ in GSM coordinates exactly the pattern that we predicted. So that was, for a long time, it was thought that this was the cause of the semi-annual variation. Just as a side note, it turns out that there's another effect called the Equinoctal Effect. And it turns out it's another angle. It's the angle of the dipole towards and away from, you can't see my hand, away from the sun. And it's—
We can see your hand, actually.
Oh, yeah. Sorry about that. the strongest interaction occurs when the magnetic equator is presented to the solar wind directly. In other words, the angle is 90 degrees between the dipole and the sun. At any rate, that's called, and it's about equally effective as the Russell-McPherron effect in enhancing activity at the equinoxes. But it turns out that if you start day-side reconnection and you have time delays in the system, you will not return magnetic flux to the X line here as fast as the solar wind is cutting it open. So you get this process of erosion from the original solid to the dashed line that alters the shape of the dayside magnetopause and a part of the tail behind the Earth. And you see that it has a larger flaring angle to the solar wind coming in. And that means that you have to have stronger dynamic pressure, magnetic pressure inside to compensate for the increased dynamic pressure. So in other words, the magnetic field has to increase in this region, which means that the current down here has to increase as well to account for that. Further from the Earth, of course, the boundary becomes parallel to solar wind. But in order to, because it's parallel, there's no magnetic field inside to balance it out. And it turns out that you just increase the radius of the tail and don't change the field strength. So this region is a region in which erosion will cause an increase in magnetic field in the tail. Well, here is the original Dungy concept, a little bit more elegantly drawn. This is merging on the day side at a given rate, d phi dt, transport tail, reconnection in the tail, return in the plasma sheet. If all of these are equal, you have a steady state. And it turns out that does happen. We discovered it a number of years later. We called it a convection bay, but today it is better known as steady magnetospheric convection or balanced reconnection. And the important point about that is that you have to turn the IMF southward. It has to be moderate velocity, moderate magnetic field, and it has to be extremely steady. The magnetosphere will really go into a state like Dungy envisioned, a steady state. But most of the time it doesn't do that. And you have these time delays that result in the change of magnetic field configuration. And that's where we want to go next. Well, first is the concept of loading. If you're transporting flux over and putting it into the tail lobes and nothing's happening in the plasma sheet, the flux is going to accumulate. Close to the Earth, and this is the old OGO 5 observations, the magnetic energy density would increase for some time before a mid-latitude onset, positive Bay onset, and then it would decrease afterwards. So this is called loading and unloading of the magnetotail, and it's just simply that phenomenon that I mentioned that to stand off the dynamic pressure, you've got to increase the internal field. If you look over BZ, it also causes changes in the direction of the field line. And you see here, BZ decreases dramatically up till expansion onset. And then you have this sudden recovery or rotation to a more dipolar configuration that occurs in the tail. So these two things, increase in B, the BX, and a decrease in BZ are growth phase consequences of adding flux to the tail lobe. At this time, part of the argument against the growth phase and loading, unloading raised by Akasofu was, he says the system's driven by the solar wind. And so in 1981, I actually got Bob Clower, one of my students, to look into the problem. And what we found is that a remarkably high fraction of the AL index, that's the measure of substorm activity at midnight, is predictable from solar wind electric field, or at least rectified electric field, VB south. And so recently I worked with Brian Anderson to look at the response of field-aligned currents to the solar wind. Here I'm using the best coupling function for AL index. Think of it as VB south, but it's more complicated. You see here on the day side, red, it rises earlier. This is the response, remember, of a field line current to the solar wind. On the night side, there's a time delay, and then it begins to decay away. And then notice this, the red line overtakes and is on top of the blue line, suggesting that magnetic flux is returning to the day side. It's gone from the night side, and we're still seeing some residual effects on field line currents. If you look at it the other way, let AL index be the input and upward field line currents from ampere, the output. You see it's kind of a delta function, about 30 minutes wide here at, or even, yeah, about 30 minutes half width or 20. And it says that it's kind of a one-to-one relationship between AL, that's the westward electrojet, and field line currents. In other words, the electrojets are being fed by field line currents driven by the solar wind. In fact, look at this number. It's 73% of the variance in the field line current is predictable by the solar wind. And of course, almost an equally good AL to field line current relationship here. The next thing that happens is as you add magnetic flux to the lobe, you increase the lobe magnetic pressure. That's pushing together on the plasma sheet, and you'd think that it would start to thin, which it does. But it turns out a quantitative calculation, it can't thin enough. Instead, think about the need for magnetic flux on the day side. As you're reconnecting around there, you're in essence creating a vacuum that's sucking plasma and field lines out of the inner edge of the plasma sheet. And so the combination of enhanced pressure in the lobes and the removal of magnetic flux makes the plasma sheet thin. And this is some early work that we did in which you see particle fluxes and then they recover their background and then they recover. And if you look at this, this is ions, protons, this is electrons. If you look at the loading of the field, drop out of the particles in the plasma sheet, unloading of the field, and they recover. In other words, that was evidence that the current sheet was thinning during the growth phase. And here's another piece of work I did using a rather phenomenal incident in which the solar wind velocity just rotated and just swept the plasma sheet across the icy spacecraft. And what we saw is the IMF turned southward, and we saw, using a Harris current sheet model, we were able to infer the half width of the current sheet and the location of the current sheet relative to the spacecraft. Here we crossed it. And what we found is that the expansion phase of this substorm, 1054, began after the sheet had thinned to the noise level of our calculation. In other words, it appeared that the onset of reconnection in the tail was a consequence of current sheet thinning. Well, another thing that has to happen as a result of all of these changes is earthward motion of the tail current, or at least the inner edge of the tail current. And the one is you had to increase the current across the tail to account for the B field above it. But the other is that the solar wind is pulling hard on the outside of the magneto tail, and the Earth has to compensate in some way. The way it does it is by the force of interaction between the Earth's dipole and the gradient in the tail field across that, along that dipole. And so what it does is it moves, first it increases the current, that helps. Then it moves the inner edge of the tail current closer to the Earth in order to balance the forces on the outside. And you see that here, the consequence at synchronous orbit. This is the east geosynchronous satellite over Chicago. And you see that when we have a growth phase, the radial component, which is negative, is becoming larger and larger negative. That is, the field is tipping over and pointing earthward. At the same time, the horizontal component is decreasing. That's a rotation from dipolar towards tail-like field during the growth phase. So that's a consequence of this earthward motion of the tail current. Also, notice this. There's a very large, as the expansion phase goes off, all of these things reverse. You get a rotation back to a more dipolar state. And associated with it here is a positive perturbation in T, D, east component, or over here, a negative perturbation, which are characteristic of field line currents. But this is a scene at synchronous orbit. Well, when the cluster spacecraft was launched, Dan Baker and I looked at some of the data. And first, look at here, this upper diagram shows cluster was basically midnight, 20 Earth radii behind the Earth. And over here are observations of total pressure and plasma pressure and blue and magnetic pressure red. And what you see here is loading of the tail lobes. Now, we're not in the lobes, we're in the plasma sheet, but because we're measuring, we assume vertical pressure balance. This is the loading of the tail lobes. And then you see a sudden unloading at this point, 407. Look at the second panel here. And what you find is a gigantic southward burst of plasma flow, 500 kilometers per second. And associated with it is a negative BZ. That is exactly the signature of an X line if you're tailward of it. It is something moving tailward very fast, carrying southward pointing magnetic field. Then you notice that the field turns, the flow turns earthward, and the magnetic field recovers and is positive. But it's still a fairly fast flow. That's a characteristic of the earthward side of a reconnection line. So over here are the observations of the actual fields and flows. These are the black, thin black lines are the flow vectors. Blue are the magnetic field vectors, and red are field line currents. The first thing you notice is it's not lined up with the geometry you really normally expect. In fact, this is not the classic picture of Ed Holmes of, anti-parallel lines coming together in the center of the tail. This is something much more complicated. It's the formation of a flux rope. And that, why? Because it's got current flowing right along the magnetic fields. But now you see here in the second diagram, that burst of tailward flow. Earth is to the top in these diagrams, dusk to the left. And then it fades right in here, and it begins to be earthward flow, which you see spraying out in this example. So this was, in our opinion, we caught an X line form earthward of us, and the X line's effect was to unload the tail. and it sent something down the tail, which was the flux rope, and it sent other things, flows toward the Earth. Let me get the next slide. I was trying to find the time on my machine. Can you tell me what time it is? Because I can't see it on my screen.
It's just about 40 past the hour.
Okay, good. It'll work just perfect. Okay, now let's think about what's going down the tail. And Ed Holmes drew something that he called the plasmoid. And it was viewed as like a slingshot with a nice smooth stone in it. And the smooth stone was a bubble of plasma that had been reconnected and was being pulled out of the tail by southward pointing hairpin-like field lines. But it turns out they're more complicated. They're flux ropes wound up in helical patterns and things, connected at one end to the Earth and the other to the solar wind. But if you're downstream and this plasmoid goes over you, what you will see is very strong tailward flow with a southward field. These fields all point downward in here. But if you're up in the lobe, what you will see is a compression of it's like a snake swallowing an egg. You'll see a compression of the magnetic field and a tilt in the field line. First, BZ will tilt up and then BZ will tilt down. Here's an example of BZ tilt and the field strength. Jim Slavin called these traveling compression regions. And he did a lot of extensive studies of the relation of these in the tail with several spacecraft. IC3 and then later GeoTail did them. What they were able to do using the speed at which it went by to calculate that it was released at 20 to 30 Earth radii at expansion phase onset. Now, of course, that's a pretty sloppy timing and all of that, but it was his conclusion that the plasmoids were released, or flux ropes, and went down the tail after the expansion onset. Well, this is some work that I did with Themis data, V and BZ. And what it shows in the top panel here are bursts of earthward flow. This is the other side of the X line now. And these bursts come in as much as 500 kilometers per second or so. And guess what's associated with them? Northward BZ. In other words, these bursts of high-speed flow are carrying magnetic flux towards the Earth. Well, that's what you expect from a reconnection site. You've closed the field lines and you've got to return them to the day side. So here's the example. This is a 12-hour interval when Themis was at apogee at about 10 or 11 Earth radii. And you see 1, 2, 3, 4, 5, 6 different events during that interval, shown by the vertical dashed line. So it's quite common when you have strong solar wind coupling. Down below is a plot of the probability of seeing either a fast flow in this diagram or a dipolarization, as these are called, of the magnetic field. And you can see that it's just inside the apogee of Themis orbit and biased a little bit towards pre-midnight. Up here, I have used the arrival of these fast flows as epoch zero in a superposed epoch analysis for the solar wind. Here's epoch zero. And you see the buildup of the solar wind electric field for some time before the fast flow arrives, and a reduction in the solar wind electric field about the time. This is a persistent feature in all the superposed epoch analysis, is that you seem to see a reduction in solar wind coupling at expansion onset. At any rate, over here, the AL index, again superposed by arrival of a fast flow. And what you see is the AL growth phase before, and then a sudden drop as after the fast flow arrives. The conclusion seems pretty obvious that the reconnection site in the tail is sending all of this earthward, and it's driving the westward electrojet. Well, this is a complicated diagram, and it's out of one of my most recent papers. I'll go through it slowly because you may not believe in statistics. These are example substorms. There's 1, 2, 3, 4, 5, 6, about 10 or 12 substorms during this page. And I know they're substorms because I have auroral luminosity, and I have movies of every one of these events, and I can see the brightening of the aurora, the propagation of the auroral surges. And so this timing is quite accurate. So let's start at the top. Coupling, 3 intervals of moderate coupling up to 2 or 3 millivolts per meter. Almost continuous negative Bay activity with weak enhancements at different times. And then at mid-latitudes across the United States, Fredericksburg, Boulder, and Fresno, you see PI2 pulsations. And associated with, let's take this major onset here, you see a burst of really strong PI2. And so now let's go to luminosity. Can't get anything in the first two because the sun's still up in eastern United States. Here, the first station comes into nighttime, and you see associated with this flow a burst of luminosity. Associated with this big one, another burst of luminosity. In fact, you can see that each of these from here on can be associated in some way with some change in luminosity. But let's look down below to flow speed at Themis. There's 3 spacecraft in this diagram. And you see burst of luminosity, a weak earthward flow. This another burst here, earthward flow, earthward flow, earthward flow, earthward flow. You come to the conclusion that these sharp increases in luminosity are a consequence of the arrival of a fast flow at Themis orbit, 10 Earth radii. If you look at the bottom line, guess what? They are bringing in magnetic flux. And you can see this one was a 3-step process in this interval, 1, 2, and a massive one here. Then here's another one, and so on. At any rate, the conclusion is inescapable that sharp changes in luminosity associated with auroral expansions are closely associated with the arrival of fast flows carrying northward field. Here's what the aurora looks like in a kilogram. The vertical axis is magnetic latitude, time on the horizontal. This is the intensity of the aurora on a central meridian of the all-sky camera. It's what's happening directly overhead. And you can see something very interesting. First, this interval is completely quiet everywhere poleward, except for this one dim growth phase arc moving equatorward. Here it's moving equatorward. Here it's moving equatorward. So this is a auroral expansion. It's a weak one. In fact, this is what we call a pseudo-breakup. And if you look back at that other diagram, you'll see that things were quite weak associated with it. So these are growth phase equatorward motion of the polar cap. That is expansion of the polar cap as you add flux to it. Now here's a very big unloading. The X line moves down the tail, and then it sort of stalls here, wherever this maps to, and you get a sequence of poleward boundary intensifications. And now up comes coupling, and you get another growth phase arc moving equatorward. But again, I emphasize that the sky is void of aurora when you have a growth phase going. Well, we're talking about substorm expansions now. And one of the things that you see during the expansion is magnetic perturbations at mid-latitudes down here. And if you look at the pattern down here in the lower left, the dashed line is the north component. And it's kind of a Gaussian shaped pattern. This went up to 60. More typical is 6 to 10 nanotesla. This is a gigantic one. And the east component has a positive perturbation and a negative perturbation relative to the center of the H perturbation. And what happened was, my interpretation at the time was that the tail current was diverted out of the tail through the ionosphere as a westward electrojet back out into space to complete the path. And when you look down on this from above, it looks like a wedge. And in particular, this is an equivalent current corresponding to closing this across and eliminating the tail current in that region. So the tail current, the substorm current wedge producing this pattern on the ground is a consequence of diversion of tail current along field lines. And then the question is, what's happening in this region? Well, I just showed you what was happening. It's the arrival of a flow burst carrying magnetic flux that's piling up in this region, as well as being slowed, decelerated, diverted, and then piling up to alter the distribution of plasma pressure and flux tube volume. Remember, you're bringing flux in. As you bring flux inside, take a spacecraft just sitting here. As you bring a flux inside, you change the mapping of the field line that you're sitting on. And in fact, if you think about it, you'll find that the footprint of the field lines move poleward. In other words, the accumulation of magnetic flux in this region will cause poleward expansion of the aurora. And the question is, what is the physical mechanism for diversion? Well, I mentioned them: deceleration, diversion and bending of field lines, and then this cross gradients of plasma pressure and flux tube volume. So those are the causes of this field line current system, and presumably part of the cause of the auroral expansion. The rest of the expansion, of course, is accumulation of stuff here on the night side in a blister of plasma. Well, one of the things that you see when this happens is at synchronous orbit, if it's near midnight. And this is an example of ATS data. What you will see here is the V component going down, the H component, it's becoming more negative, the H component becoming weaker, a substorm goes off, and here's a positive D perturbation, and this satellite is at midnight here. So this is pre-midnight. That's what you see on the ground, a positive perturbation in D. Here's what you see post-midnight, a negative perturbation, identical to what you see on the ground. And the conclusion I came to when I first saw this is that the pattern on the ground and in synchronous orbit is the same. Therefore, the currents must be flowing on field lines outside of synchronous or above the synchronous spacecraft. That's the origin of it. Now, associated with these arrival of these flows are electrons and ions in the leading edge of these flow bursts. And it turns out that these flows are not steady or anything, that they're very bursty on a few minute time scale. And it's the leading edge of each burst. So a bursty bulk flow is 10 minutes, 15 minutes long, but within it are these little fast flow intervals. And the leading edge of those interacts with particles in such a way as to energize them. So you're getting particles from, tens of keV up to several hundred keV are being injected in that region, which is going to form the current wedge. And if you're far to the west, you'll see only ions come in as dispersionless. If you're far to the east, you'll only see electrons coming in as dispersionless. dispersionless means that all energy simultaneously. But in this region, which is the current substorm current wedge region, they're simultaneous. Well, let's go back to the processes that I started the talk with. And the words that you should remember are coupling, reconnection, erosion, transport, loading, thinning, earthward extension, and then expansion phase. Reconnection, plasmoid ejection tailward, bursty bulk flows earthward, substorm onset, the auroral expansion, the current wedge, synchronous dipolarization, and particle injection. So it all fits together for an isolated substorm. It gets a lot more complicated when you drive it continuously and the plasma sheet is thin most of the places in the tail, and you have these flow bursts coming by, expanding the plasma sheet and in certain regions and so on. So I haven't tried to give you a theory of that, but I think it's basically the same processes as you see here. One of the things that I discovered in working on the simulation of the event that I just showed you with all those panels on it is shown here. This is what I call my bifurcation index. What I do is I simply scan the information about flow speed in the neutral plane of the current of the plasma sheet for a boundary, which I've determined 250 kilometers per second is the best one. Here, that's a high-speed flow where it's red. Then it becomes slower. Then it goes to 0. That's the rope. Then it gets stronger again in the opposite direction, and finally 250 tailward. And that that dividing line between high-speed flows in opposite directions, I call the X line. This is 40 minutes before the onset in the simulation of a major substorm. I showed you before, actually, the data for it. And in fact, in this simulation, there was never a time in which there wasn't at least one or more, and typically 4 or 5 X lines simultaneously present. The simulation just shows the tails reconnecting all the time. And so the question is, what is happening that it appears in the auroral observations and in my study of the data? We don't see loading, unloading events. We don't see lots of tailward flows with the spacecraft that we have out there. It almost seems to me as if the data are saying that there's a quiet interval in which not much is happening in the tail, and then there's an explosive reconfiguration through reconnection. I think that this is the biggest question from my point of view, and how can this simulations be so different from my feeling about the observations? These are just some of the questions that I would like to answer for myself. Why is the expansion onset time and location so unpredictable? Well, that might be just chaos theory. Why is so much of the AL index variance predictable by the solar wind if it's an unloading event with an unpredictable onset time? Why are onset indicators not precise or sometimes missing? Sometimes I don't see the mid-latitude bay. Sometimes I see it and not the auroral zone bay. Maybe it's just station location effects. Why are onset indicators not precise? Oh, I got that. Why are auroral signatures of fast flows at onset so hard to find? I'm basically saying that a fast flow comes in and that causes the expansion onset. But it's been a continuous argument of the opposition that there's no evidence of the fast flows. In doing this work that I've just reported to you, I found that there's problems. There's too much moonlight. There's too much reflected light on the inside of the dome. There's too many fixed lights outside. So what I did is develop some, using image processing techniques, ways of removing those effects, enhancing the information. And I was able to find a very weak evidence of flows starting just a little bit poleward of where the aurora breaks up, in other words, close to the Earth. But what does the fast flow at onset trigger an instability? Some people think that the reconnection has nothing to do with it, that it's an instability of the plasma distribution. Is the plasma sheet truly inactive? That's what we were talking about. Why does the X-line form on the dusk side at about 22? Why do simulations reconnect continuously? Those were my questions. That's the end. Thank you.
Thank you, Bob.
Yeah.
It's an excellent talk. There are 2 times in my life where I've been able to convince myself that I understand substorms. The first was after your AGU talk, and the second is right now.
Well, thank you for that. You know, there was somebody that Jimmy and I know very well at UCLA. It was, well, both Fred Coroniti and Charlie Cannell were people with golden tongues. And I remember that I would listen to them and I'd say, oh my God, I understand it completely. And then I'd walk away and try and explain it to somebody else. And it was clear I didn't.
Well, that's why I'm recording it now.
Okay.
Anyways, you know, I want to give other people here a chance to ask questions, but I want to sneak in my own here too. I'm wondering, so you know, I've heard people talk about you know, northward IMF turning and substorm onset. What's the physical mechanism there? What's the link?
In fact, every single superposed epoch analysis of coupling or BZ shows the same thing, a peak at substorm onset. To one extent, that may be a consequence of just the superposition process, ensemble averaging. Remember that you've lined everything up by the onset. And let's suppose that the southward turning is a square wave, and it turns southward 2 hours before, 30 minutes before, and so on, and simulate. So you have at the time of the onset, you have all of these things are southward, but the times of southward turning and the times of northward turning are offset and sort of uniform and cancel each other out. So what do you get in the superposition? You get a peak at expansion onset. That's one suggestion as to what it is. It has been argued that it doesn't have a physical basis. And I'll tell you, I think I know what's going on, and I'm going to have a paper in about end of May that I'm going to submit. But I'm not going to tell anybody until then what I think's the cause of the misunderstanding of this whole business. And I think it'll be physically reasonable. So I'll let you go at that point on that one.
Okay, great. Well, thank you. Okay, so you know, people feel free to jump in here with questions. You can also, I guess, raise your hand or type in the chat or whatever you feel you want to do.
Jimmy, you must have something to tell me.
Pardon?
Jimmy, do you have any questions or comments?
Oh, we've talked so many times.
That's true.
I thought I'd leave the controversies out here, right? I mean, there are, of course, you remember that GEM meeting 20 years ago when I actually had a vote on who believes in the near neutral line model?
I was shocked out of my mind. Explain to the people what happened.
And over 50% actually did not believe it, you know, and I think the evidence still exists, right? I mean, maybe you can comment on that. I mean, what do you think about the fact, you know, that if you look at the first brightening, you know, it just maps way too close to the Earth? I mean, do we have an explanation for that, or do you have an explanation for that?
Well, I think that the mapping close to the Earth is the arrival of a fast flow, and that the X line is fairly near Earth, but I cannot explain why we so infrequently see any evidence of a flow between the two locations. That's the real problem. And to some extent, it may be the luminosity. There's also another thing that people don't really take into account, and that is an all-sky camera is a fisheye lens. And when you start looking at the distortion of the sky that occurs in the, you have a rectangular square grid of pixels, but it's not square in geographic projections. It's a real mess. As you get out away from the zenith of the camera, you begin to get tremendous distortions that make it hard to see things. For example, when I join two images together in the all-sky camera, I will see a brilliant streamer coming out of the boundary between the two, and I'll barely be able to see it in the other image. And in fact, I have an example in which I have two streamers simultaneously present. In the poleward camera, I see it very clearly on the eastward side, and can't hardly see it in the other. And it's just vice versa on the other side. So there's obviously things to do with aspect at which you're viewing, relation to the sun and moon and all of that, that makes these observations very hard. I think what I wish we had was high cadence, spatial resolution cameras in space. But when I mentioned that to Dave Sybeck, his answer was, been there, done that.
Well, they're actually coming. I mean, the SMILE mission will have a UV imager, I mean, with similar capabilities than Polar had or Image had. So we will still get something. But I mean, what bothers me a little bit, and you probably know that better, I mean, is 20 years ago, we didn't have the data. But now we have Themis, we have lots of observations, I mean, between, let's say, 6 and 10 RE and the tail, the line of apsides is lined up, I mean, with the ground observations. I mean, hasn't anybody tried to find that? I mean, you said the bursty flows are it, right? I mean, you should see the bursty flows, I mean, coinciding, I mean, with auroral brightening in the kilogram.
Well, I see them. But I don't know about other people, whether they think it's true. I've done even statistics on it. But I think part of the problem is it's not all that easy to process the auroral image data, and people have been a little slow to do it. But in my opinion, there is basically a one-to-one correlation between the arrival of a fast flow and a luminosity enhancement.
Okay, so you say opinion. I mean,
well,
I mean, I'm looking for the hard evidence. I mean,
I haven't published that.
Okay. So in other words, there's still something to do for the graduate students here, right?
Yeah.
Left something over. That's good to know.
Any more questions?
Hi, yes. I was wondering if you had any comments about the distinctions between isolated substorms versus steady magnetospheric convection versus quasi-periodic substorms, aka sawtooth events. Do you have any feel for what pushes the magnetosphere into one or another modes?
The isolated substorms are produced by fluctuating, well-isolated pulses of coupling. You go through this whole sequence that I've talked about. Steady magnetospheric convection comes out of a substorm that has gone off, but the IMF remains southward. Coupling remains constant with very little fluctuations in it. So that's exactly the situation you'd expect. There's nothing changing dynamic pressure or the electric field to trigger any kind of expansion. So it just goes into steady on the day side, steady on the night side. As long as you've had more than a substorm time scale to set up the condition, you can get into that Dungy state. But you drive it too hard and it just can't apparently manage it. So I'm of the opinion that the sawtooth is very much harder driving of the system, and you just can't get into that balanced reconnection state. that's all I have to say on it.
Okay, thank you.
Anyone else? No, we're just a little bit over the hour here, so
Well, then it's lunchtime for me. Actually, it was lunchtime an hour ago.
then we won't keep you any longer. But just thanks again, Bob. It was an excellent talk, and we appreciate you popping by and sharing.
Okay, Jimmy. Kevin, I can never pronounce your last name. Can you tell me?
Genestretti.
Apparently not try. Genestretti. Okay. Thank you. All right. Bye, guys.
Great
Hey, Bob, thank you.
Uh-huh.
Excellent talk.
So I'm going to sign off.
Okay, have a good one.
Okay.
Uh-huh.
Bye-bye.